All right, well, welcome everyone. There we go. All right. I'm doing this a little bit differently today just so there will be a recording of the lecture, even though the lectern doesn't seem to be set up anymore to handle YouTube Hangouts on air. If it's too fuzzy, I might end up switching over and just using PowerPoint on this computer, in which case there might not be a recording of it, but you're all here today anyways. So it's always a pleasure to have, this doesn't always happen, but your very first class of your new program, and to be standing here welcoming you not only to our class, but to our program, which really is a great pleasure. This is Principles of Biostatistics, and it will be your first of at least 3 biostat courses that you take, whether you're in the EPI or the BIOS program. I'll teach you for this one along with Tony DeVito, who is in the back here. And then next year, for most of you, probably next fall, I'll be teaching you again for biostatistics too. So, but this semester, we're going to start really from the basics of biostatistics, assuming that that you have no biostatistics, or if you did have it, it was from a long ways back. And the point of this class is to help get everyone up to the same point where you're ready to then start next semester, where you'll start getting into some more advanced topics, and then by your third course covering scarier things. But this is a fun course. I try to keep things fairly conceptual, as you'll see today. And the basic format of it is every week I'll go up here for about an hour to give the lecture. The lecture will be big picture. There will be lots of pictures and discussion, a few formulas, not too many. But then after the lecture, Tony will take over and we'll do a lab session, and that's where you will put to practice the things that we talked about in lecture.
Yes, you're back here.
What's that?
The air conditioner is blowing. Yeah, you're welcome. Once we get more.
I'm not sure why we're still getting a spinning wheel here. But I think it might be time to abandon our recording of this lecture and what's that? I feel like it would take too long to get set up. Yeah. And
we can actually use a previous recording.
Yeah, we could. But today is pretty basic anyways. I suspect that not many of you are going to want to rewatch this lecture anyways. But this does bring us to the general format of the course. All of the lecture and lab sessions will be recording and streaming live. So after today, for all of the regular lecture and lab sessions, it will be up to you how to digest the material. You can come here like you have today and take in the class in person. You can stay at home and watch as it happens live, and there will also be it's set up with a chat window so that you would be able to ask questions during class as well. And there will be another link also for the lab sessions. Or you're all graduate students, you're all adults, you can do neither. If that time is difficult for you that time, they will be recorded and available to you. So you can watch them sometime later. So both the materials and the lectures and labs will all be available to you to take in the way that is that works the best for you. I'm tired of the spinning wheel, so I'm just going to move us over here to this. That looks better. So some basic things that we hope to accomplish today. You've already accomplished the first things, the ability to find your lecture and lab room for this class. Congratulations. We're going to talk a little bit about SPSS and our software, some of their pros and cons. And I'll invite all of you to choose whichever works best for you. Essentially, SPS is a basic piece of introductory software that allows you to point and click and accomplish the things in about the easiest possible way, and that's what Tony will be using in the lab sessions. But I'll also encourage if you are keen or you already know SPSS and want to start learning something different, to start learning our software, and I'll support that along the way and help people out who want to do something extra and something that will come in handy later in the program. We'll go over the syllabus in a little bit, and then get on to a little bit of actual biostatistics content on types of data and types of graphs for describing those data. We have a textbook, and I call it required because, because it's free anyways, so you might as well have it. It's actually a very good textbook. When we moved over to it, we moved to it not only because it was free, but because I think it's actually one of the best introductory statistics textbooks that is out there. But it's pretty convenient. You can just download a digital version for free, or if you go to the website, there are a few options for ordering a low-cost print copy if you want to have something physical. The prices they change all the time, so they're probably a little different, but they're not much. And I just wanted to introduce a bit about myself as well, so you know what my background and interests are. My main area of research is in what they call high-dimensional statistics. This is the area of statistics where we have more variables than observations. And this happens commonly in genomics, and cancer genomics is my main area of research. Human microbiome and predictive modeling in those contexts. So the typical data analysis problem, we have some dozens or hundreds of patients, and then we have tens of thousands of measurements of different genes, or hundreds of measurements of different microbiota on each of those people, and we want to associate those with disease or with outcome from the disease. And if you're interested in more, I have a website up that you can take a look at. I just wanted to mention that I organize what we call a statistical learning book club. Occasionally we do data competitions, but in recent years we've done more of reading textbooks, and we've been collaborating with the statistics department at the University of Salzburg in Austria to essentially pick a textbook and read through it section by section. We pick interesting books that are more conceptual than hardcore math, but try to find things that are outside of really your basic statistical topics that are covered in the program. So we cover things like high dimensional data, predictive modeling, Bayesian statistics, interesting things like that. So if you're interested, please let me know and sign up for our Google group here. We'll probably start up again in October. And finally, just to say I have an active research group, and I'm always looking for students who are interested in bioinformatics or data science and genomics and cancer research, microbiome research. So if you're interested, let me know. I'm usually supervising field work and capstone students, and sometimes do have positions available as well. So our expectations for you in this class, we expect you to ask questions, and they're warmly welcome. They make everything more interesting and enrich the experience for everyone. So I hope that at least once we get warmed up, you'll feel very comfortable just putting up your hand and asking questions as we go. And we expect that you will be interested in the practical aspects of data analysis as it applies to public health. We will have 2 exams. They're on the syllabus. They're non-cumulative, so they will only cover up until, or what was covered since the previous exam. So the first exam will cover the first part, the second exam will cover the next part. We'll also have 6 homeworks, and then something that's more fun than a final exam, we'll have a project, and on our last day there will be a poster presentation of those projects. So I'll post soon some more details about that, but you won't get started on the final project for another couple of months. You can expect that we'll have class will get started fairly promptly at 5 p.m. every day, and will end promptly at 7:50 p.m. every day because some students may have another class at 8 o'clock. We will be available to you through several channels. I haven't actually created it yet, but I'll create a Google group because I find it easier to use and reply to than the Blackboard discussion groups, and that's intended for questions of general interest. So if you have a question like, I don't understand question number 2, or something about the exam that I didn't understand from what was going to be announced, things that really other people should hear the answer to as well, please post them to there. And generally, if you email me with that kind of general question, I'll say, please post it to the group so that everyone can hear the answer. But if you have questions that are specifically about you, don't hesitate to email me about those kinds of questions. I don't hold regular office hours because I found they're difficult to hold at times when a lot of people are going to come, and I think it is more effective just allowing people to book individual meetings. And I try to make this easy through this website, calendly.com. You can just go there, see when I am available, and just book a meeting, and I will confirm it, and we'll have a meeting. It can be either in person if you want to come here, or by telephone or Skype or something like that. And finally, you can expect a supportive learning environment in here. Neither Tony nor I nor any of your fellow students are ever going to put you down or make you feel bad about asking a stupid question or anything like that. We fully intend to make everyone feel comfortable and supported to learn as much as you can. And if you're having any sort of problems that are interfering with that, or complaints or feedback, don't hesitate to let us know. We want to know. Actually, before I get started on what is statistics, I wanted to quickly just review the syllabus. if I can find it. Okay. So at the top, you've got some useful stuff. You've got any URLs and any email addresses that you might need. You've got your links to the reading, to the textbook, stuff about our course, including the learning objectives. So the grading for this course, it's going to be based on those homeworks. They'll be worth the equally largest chunk, 30% of your grade. These two exams will each be worth 15%. Just to give you a brief preview of what to expect, they will be in class, in person, open book exams. So you will be allowed to bring your lecture notes and your computers, and you'll be given the full 2 hours and 50 minutes of class for these exams. And then there will be this final project also worth 30%, and essentially it's going to be a data analysis to give you some practice actually both analyzing data and then communicating it. And we will provide you with some example data sets that you can use, but you're also welcome to analyze your own data set, whether it be something from work or from one of the many public data sources that are available, something that interests you. But the basics of it will be you perform a data analysis that includes some things that are from this course. So it needs to cover some of the learning objectives for this course, and then you will prepare a poster, and then on one class we will take turns. We will have everyone will get a few minutes to quickly present their poster to the class, and that's more or less how that will go. And then class participation, this actually will be based on during the final project. There will be some staggered deadlines as you go along, and you'll be asked to post components of your project every week and provide some feedback to each other on the components, so that you can't do it all the night before the final project. It will be in stages, and this participation will be based on your participation in those stages. Some boilerplate stuff, and then the class schedule. I'll let you review the class schedule on your own, but essentially we're covering the basics of statistical inference, exploratory data analysis, hypothesis testing, confidence intervals, and some regression at the very end, and some categorical data analysis while we're at it. And just to point out one more thing, at the end of your syllabus, I've included a section on statistical notation, just to provide a convenient place for you to refer back. And just as a very brief summary of this, I'll just tell you this bit that we will both use, or at least try to use, a consistent notation throughout the semester, that Greek letters will be used for things referring to populations, and Roman letters will be used to refer to samples. And I'll talk about that in the coming lectures. Okay. And now on to the start of our statistical content for the semester, and I think we're doing pretty well for time. I divide statistics into, actually first, are there any questions about anything I've talked about so far about the class, about anything before we actually dive into materials? I will point out there's been going around a verification of attendance sheet. If you haven't signed it yet, please make sure you sign it. Okay, okay. We have to do it on the first class. You'll see this in every class you go to. This goes back to CUNY, and this is how the university verifies that you're actually in the program. So, so make sure you sign it. It's important, especially if you have financial support from the college. With that, I divide statistics into these three main components of design, being the part that you do before you collect any data. Description, which is the first thing that you do after you have your data, summarizing and getting a feel for the structure of it and basic lessons in it. And inference, which is the making of decisions and predictions, accounting for the uncertainty in the information. And statistics, this is a little hard to see here, so I used to be in math actually, and math and physics, and I felt it was always a little difficult to a general class necessarily to justify how these things were going to be useful to them. But I never feel like that in statistics, because statistics is used all the time in all areas, anywhere where there are data. And the history of it goes back at least to 450 BC, when the use of things like averages started, or at least we have records of those being in use. And I find it very interesting that some of, in some areas, the things that were first discovered and in use at the beginning of a field and thousands of years ago, they got replaced by the next thing as time went on. Certain basic things in statistics, that's not the case. The things that were in use early on continue to be the fundamental things that we use today, like mean and variance. Let's start with some definitions now. So I'll be referring lots to populations and samples. And when I say population, I am referring to the entire group of interest. And it might not always be obvious what that population is, but it's an important thing to know, because when you perform inference, you're performing interest about that population, whether it is everyone in the world, whether it's adults in the United States or residents of New York. It is that entire group of people who you would like to study. But in general, we can't study all of them. What we can actually study is a sample, that is some subset of that population. So in this example here, London has been voted one of the world's favorite cities, but let's see, New York was, I think, one the best place to do business. In this example here, what is the population that that they're trying to make inference on? I say make inference on because they didn't ask everyone in that population, but still they're making some conclusion about it. Yep. Yeah, maybe the entire urban population, maybe actually the entire everyone in the world. It depends on how they did their sampling. Just by looking at the you know, the title of it, at least, this global survey of world's favorite cities, I took it to mean to be everyone in the world was who their target population was. Obviously, they didn't ask everyone in the world. They had some sampling strategy to ask a subset of them in a way that they hoped would allow them to make an accurate inference about everyone else. Just as a note, when we do survey the entire population, this is called a census. We have one coming up in a couple of years in the US. And one more definition here, one single observation in that sample, we tend to call that a record. We will have a little bit of the design aspects later when we do power and sample size calculation, but I'm actually going to start here with exploratory analysis and descriptive statistics because it's a nice way to get into familiarity with data, and it's the place where as a data analyst, you often are brought in at the period of analysis rather than those earlier points of design. The purpose of descriptive statistics is to try to communicate or understand the data visually in a summarized form that will allow you to interpret in ways you wouldn't be able to just by looking at spreadsheets or tables of numbers. This is a very famous statistical plot from 1866 from here in New York City before there were computers. But this is a nice example of how first, it is a very basic kind of plot. This is just a line plot. It is showing the number of deaths per 100,000 population over time. And you can just see it going up and down and with a few spikes. They've done an excellent job here of annotating it in ways to help you understand what these different spikes are. So you could look across and see what epidemics affected New York City back during this time and how much of an increase in the death rates they actually caused. And there are other nice features of this, such as annotations of the axes, and we actually have two y-axes here, the deaths per 100,000. Oh, it's the same on both. It's just labeled on both sides to make it a little bit easier to read. So this is another kind of plot that you will be making and will be using this semester and later. Inferential statistics, where we actually make inference about the population. This is a nice example. It's, I would say, a combination of exploratory and inferential statistics. The inference here, so this is a plot that I find interesting to check back on every now and then, the popularity of Trump by multiple polls on the 538 webpage. The data points here are actually individual surveys, so they aggregate all of the different surveys being done, and then they plot an average here. They do a bit of weighting and adjustments for the bias of the polls, and then they put confidence intervals around it. So this confidence interval is intended to give you some idea of the uncertainty in these, and then the inference here. One potential inference would be whether there are different numbers who approve than disapprove. But to make inference like that, you have to answer questions like it's not enough just to know that there is a difference in the disapproval and approval ratings, but you need to know how great is the uncertainty in those estimates and what are the sources of uncertainty. And specifically, those sources of uncertainty, are they causing random or random uncertainty that's equally likely to be higher or lower than the true answer, or are they biases that are tending to take you in one direction or the other? Some examples of inference that are common in public health would be things like, does an experimental treatment for cancer work? There's a yes or no answer to that. So do the people given this experimental therapy have a better outcome than people who are not? Cycling in the city, is it becoming more dangerous, or is it just the same over time? Does some public health issue like this, is it different in different parts of the city? So spatial kinds of questions, or any other ones. And feel free to post them if, especially if you have some that you are thinking of for projects and are wondering if there are data for them. I will be distinguishing the different methods that we learn this semester by the type of data that they're intended for. So the first thing to understand about your data set is going to be, what kind of data do you have, or do you have more than one of these? We're going to call them nominal data, ordinal, discrete, and continuous, and I'll talk a little bit more about each of those. Starting with nominal, and the reason that this is called nominal data is that they are nominally even data, or they're nominally even numbers. In fact, they're not really numbers. An example would be a study that categorized its participants as either male or female. This will get coded in the machine as zeros and ones, but in fact those numbers are arbitrary. They're not really numbers. They're just representing some descriptive variable. So among the nominal types of data, there are binary and there are categorical data. An example of categorical would be blood types, because there are 4 of them. And one possible coding of them would be 0, 0, 1, 3, 4. It's about as arbitrary as any other. But these are only nominally numbers. They're really references to things that we describe in words. Ordinal data are like nominal data, except that they actually have an order to them. So with the nominal data, the order is completely arbitrary, whereas with ordinal data, there is some ranking of them. An example being this Karnofsky performance scale, which is a clinical description of how mobile a patient is, ranging from fully active, which is called a 0 on this scale, to disabled and unable to move on their own, being a 4. So here the numbers are again arbitrary. They're not, these are not numerical things, but there is an order to them. So with ordinal data, the order is important, but the magnitude is not. So the difference between the difference between 0 and 1 is not the same thing as the difference between 3 and 4. The difference between being fully active and can do light work is not the same thing as the difference between being ambulatory less than half the time or disabled. And one important type of ordinal data are rank data, such as the position of finishing a race or something like that. So one example of a rank variable would be the ranking of different diseases for the number of deaths that they cause. So not the actual number of deaths by these diseases, but the rank of them. So in 2010, heart disease was the leading cause of death in the United States, followed by cancer, and then followed by chronic lower respiratory diseases. And you can see here what I'm talking about, how the order matters, but the difference in magnitude is arbitrary. So heart disease and cancer are very similar, but then there's a big gap between 2 and 3. So with ordinal and rank variables, magnitude, the order matters, but the magnitude does not. The magnitude is arbitrary. So discrete data, these are integer or count data. These same data could also be considered discrete data if we're looking at the actual numbers. So the 590,689, that is a discrete or an integer variable. And looking at a full table of these, what we have here, a little bit difficult to see, but this is year by year. And it is each year a ranking. That ranking that you saw, 1, 2, 3, 4, 5, over each year with this, this number of deaths per 100,000 and the order. So we have heart disease is number 1 every year. Cancer is number 2. The pneumonia and influenza is number 3, but these number 4 and 5 switch back and forth. So why is this switching back and forth happening? Yeah. Yeah, different amounts of disease occur. That's right, and the way I would describe that is by saying that this is a random variable, and that the actual number of deaths that occur in any given year has some component of randomness to it. So even though this is from the entire population, there is an element of randomness in that population as to how many people die in any given year. I also just wanted to point out that these are standardized numbers per 100,000. And that fluctuation in the 4 and 5 positions. I'll just note here that this discreteness, I'm going to next talk about continuous variables, but I'll just note that this discreteness is not especially important when there are a lot of possible values. So when we're talking about thousands of deaths here, the fact that these are discrete is not that important. It's more important if we're talking about small numbers, like the number of people in a household. For that, then it does make a difference whether a variable is discrete or continuous. So like ordinal variables, the order matters, but unlike nominal or ordinal variables, the magnitude matters and the rules of arithmetic apply. So this is the first kind of variable we've covered where the standard rules of arithmetic, subtraction, multiplication all apply. Finally, continuous data. These are things like time, weight, length, or mass. They can be either bounded, such as mass, it's always positive, or like weight and length, or time, which potentially could be negative before a certain time and positive before a certain after that time. But the key thing is that if there are bounds, all values are possible within those bounds. And again, the magnitude matters, and again, arithmetic applies. And I'll just say that this distinction between discrete and continuous is sometimes kind of arbitrary because it's pretty common for something like weight to be measured in, say, pounds, and within the limits of some measurement, like the scale that we're using, only discrete values are possible. So even though weight is continuous because really any value between the bounds is possible, the variable is still discrete because we can only measure it with a certain discreteness. So I'm not going to make much of a big deal over this difference between continuous and discrete, except in cases where it really matters, such as number of people in a household, where you really can't have all values between the bounds. Yes?
One question. So the discrete data would only be integers. So as soon as we move into, say, 8.2, but we only have one example. So not be discrete, even though we only allowed 8.2, 8.8.
The distinction I would make is it something that the true value can take anything? Then I call it a continuous variable, even if we measure it with a discrete instrument. So like with weight, my bathroom scale only goes to 0.1 pounds, so it can only take discrete values, but I still call weight a continuous variable because the truth of it is continuous. But as far as statistical approaches go, it doesn't matter as long as that discreteness is fine enough that it's not a major component of your measurement error.
That means discreteness wouldn't be necessarily tied to integer values, but discrete, smaller, something.
Yeah, discrete does not have to be integer. Yeah, discrete, it just means that not all values within the bounds are possible. Often both of these get referred to as like scalar variables, which is just a way of saying that they are ordinary numbers to which the rules of arithmetic apply. And a scalar variable is, I guess, what you would include discrete and continuous under, and is probably a more generally defensible terminology. Let's do a little bit of summarization of data, and I'll just say that this is extremely important because it allows you to actually gain some intuition for your data, and it allows you to avoid making terrible mistakes. And for any data set that you are analyzing seriously and is important what the answer is, you should do some summarization of it. Because if you go straight from your data to your inference, your hypothesis testing, it's possible to make mistakes that cause you to get really nonsensical results and not realize it because you don't have that intuitive look at your data. And really, no matter how far you go in statistics and how sophisticated of analyses you are doing, I hope you will get to where you are practicing your intuition for data to the point where you're not surprised by the inference that you're making, that you have enough of an understanding of your data that the results of your hypothesis testing, your inference, agree with your intuition. Or if there is some disagreement between your intuition and those results, that you can dig further and try to understand where that difference is coming from. There are numerical summaries and graphical summaries. I'll go through just some of them for each of these types of data. I'm grouping together here nominal and ordinal data as our non-scalar data types. And one of the go-to figures in newspapers anyways is the pie chart here. Statisticians tend to scoff at pie charts and not use them because we think that there are more informative ways to do it, but they're there. What's wrong with this pie chart? I thought this would be more interesting than a pie chart that I made myself. 87% yes, 13% no. Okay, I think you know what's wrong with it. So frequency tables. Here's one that we actually use a lot. Yes. Oh, okay. Yeah. What's wrong with this? What's wrong with this pie chart? Well, normally a pie chart, these areas are supposed to represent the proportions. Oh, so yeah, 87% of it should be yes color, 30% should be no. But I don't know. They just had an image there. This is probably not made by statistical software, and they just wrote it. So would have been better in this case just to write the numbers without the pie. You'll be doing lots of frequency tables this semester because these are the basic numerical summary for nominal and ordinal data, also called contingency tables, but these are fancy names to just say you're listing the total number or the total count for each number. That's all it is. An example, this is a hypothetical clinical trial that has a treatment group and a control group and a measure of the severity of pain. So it's a clinical trial for a treatment for pain, and the patients are each asked to rate their pain as mild, moderate, or severe. And these simple listings here, those are frequency tables. Those are one-way frequency tables where you just list the number of each possible value for these categorical or nominal variables. That is a so-called one-way frequency or one-way contingency table. This would be a two-way contingency table where we are representing two variables together in one table. So here we have both treatment and control and the severity of pain and just the number of counts for each of those combinations. And this allows us to immediately see something Okay, among the people who reported mild pain, most of them are in the treatment group. There's a smaller number of them in the control group. And among those with severe pain, more of them are in the control group. So looking at this, it looks like maybe this treatment is effective, but we would have to do a hypothesis test to establish whether this is enough of a difference to be inconsistent with random sampling variation. But immediately, just by making this table, we're able to get a little bit of intuition about saying, okay, these results at least are consistent with what we would see with an effective pain treatment here. And then we can go on with the hypothesis testing. What I've written along the bottom and along the side here are what we call marginal totals because they're written in the margin. They're just the sum of what we see above or to the left of them. And if I divide each of those by the total number of patients, those become marginal probabilities. That's something that you will hear as you go through statistics. Sounds exotic, but when you first hear it, but it's really pretty simple. It's called marginal. I think that the origin of it is because it's written in the margins of the table. And you can also think of it that it is, so in this case, this would be the marginal probability of being in the treatment or the control group, and it's regardless of the pain that you reported. And along this margin, these are the probabilities of experiencing mild, moderate, or severe pain, regardless of whether you're in treatment or control. So these probabilities in each cell here, these are what would be called joint probabilities because they're joint probability of the severity of pain and for each of treatment groups, whereas these are the marginal probabilities. And another way we'll be referring to these probabilities inside the table will be conditional probabilities. We'll get into this later, but I will refer to things like the probability of experiencing mild pain conditional on being in the treatment group or conditional on being in the control group. So rather than pie charts, the preferred replacement for them by most statisticians is the bar chart. These are just some very basic looking bar charts that are displaying the same things that were in those one-way frequency tables, the number of people in treatment and the number of people in the control group. Why do you think that these would be preferred to pie charts? In this situation, it doesn't really matter. These are very simple data, but let's say something more complicated, like we have five different levels of a categorical variable. What would be an advantage of a bar chart over a pie chart? Yeah.
It's probably easier to see differences across the pie chart versus the pie chart.
That's an important one. So you can really see these differences quantitatively. It's much more difficult to see differences in proportions in a slice of pie. Yeah.
Less of a categorical comparison, more quantitative.
Yeah, especially if two slices are like on opposite sides of the pie or something, you can't really compare them. I mean, you can look at the numbers, but at that point, if you're just using the numbers, you could also just use a table. Whereas regardless of where these occur here, those differences in height you can tell quite sensitively. So I'm not going to say completely rule out pie charts. They do have sort of an infographic appeal to them, and sometimes they're appropriate. But for quantitative study of categorical variables and for your own exploratory data analysis, it's more informative to use bar charts. And there you have choices of kinds of bar charts. On the last one, those were side-by-side bar charts. This is what we call a stacked bar chart, where the proportions are on top of each other. And this is a way to represent the two-way contingency table. So the one where we had both pain severity and the treatment group in the same table. That is what we're representing in here. So here, there are a couple of ways you can make this chart, but I'm showing bars for treatments and control. This shows us the thing we knew that there were equal numbers in each of those. And then we have, by the size of mild, moderate, and severe colors in each of these, the proportions. So it's a little bit more difficult to compare within, but this has the advantage of putting the two variables together in the same plot. That's not all you can do for categorical data, but that's all we're going to get to today, and I'll show you a few things now for scalar data or for discrete and continuous data. You can again use frequency tables for these by categorizing the data. So by taking bins and just counting the number in each of those bins. So instead of weight, taking something like 100 to 130 pounds and counting the number of people who are in that range, 130 to 100 or 131 to 150, and counting in there. So that is discretizing or making more discrete the data, and then treating them the same way as we did for the nominal or ordinal data. An example of doing this would be if the original pain scale were actually a 0 to 100, but rather than looking at the actual data on that 0 to 100 scale, we just wanted to divide it into these three groups of mild, moderate, and severe. And in general, of course, the smaller the bins that you make there, the bigger a table that you'll get. And there isn't really a right answer about how to divide it up. If there are too many bins, you're going to see a lot of variability, and it won't be especially informative. If there are too few bins, then you might miss a pattern that exists in the data. But this binning forms the basis also for this kind of plot, which is called the histogram. And it's really a bar chart based on the discretization of scalar data. So in this example of the pain scale, if we had pain measured on a scale of 0 to 100, I have binned them here into, see, there are 4 bins for every 10, so this is about 2.5, width of 2.5 on this pain scale. So I've arbitrarily created bins of this size, counted the number of people in each of those bins, and then made this bar chart to show those numbers of people. And it's a little bit more graphical, or it's graphical as opposed to the table, but it's the same data as we saw in that table. And to make that point that number of bins, the size of them is discrete, here's the same data with using larger bins, 5 per, and that's a subjective choice, even though the software tends to have some kind of default that it will make. In this example, this looks like what we call a normally distributed discrete or continuous variable, so that division of it into mild, moderate, and severe, anywhere that we set these thresholds is going to be arbitrary. You see it, there is not some natural place to divide mild from moderate pain. It's just the threshold put in there. And that is often the case with categorical data that is analyzed in epidemiology. You know, there are all kinds of things that are really scalar data like this that are treated as categorical data, such as body mass index, such as income levels. It is convenient to analyze them as categorical data, but you should remember that underlying it is something that is really a continuous variable. This is I'm drawing a line over here. These are called frequency polygons. You don't see these that often, but they're occasionally useful. One thing you do see probably a little more often is a smooth line drawn on top of the histogram, which can be a bit helpful for if the histogram itself is a little bit noisy, for showing what the trend is over time. It's hot in here, isn't it? This is the same variable here, but I'm adding on top of it a box. And this is a really useful kind of plot that I hope you've become familiar and comfortable with. And the box plot is great because it is both visual and descriptive, but it also has quantitative aspects to it. To understand those, I need to give you a few more definitions. The percentile is the percentage of your observations that are at or below a given value. So the one everyone knows about is test scores. If you get a test score in the 90th percentile, that means that 90% of all the tests were at or below what your score was. Quartiles are just these convenient percentiles, the 25th, 50th, and 75th. And these three percentiles are shown in the box plot, the start, the middle, and the end of that box. And these are referred to as the first quartile, the second quartile, and the third quartile. This second quartile has a special name. Who remembers what it is? Yeah, it's the median. What maybe you don't know is there's also a name for the difference between the first and third quartile. Yeah, interquartile range. Very good. So we've got these three quartiles, the median, the interquartile range, and then we have these whiskers, and these whiskers extend from the median out to 1.5 times the interquartile range above and below. That is the maximum that they extend to. In fact, they don't necessarily extend that far out. If there are no data points beyond here, then it only extends as far as the furthest observation. And then any data point that you see outside of that can be thought of as an outlier. That's a subjective distinction. There's no agreed on way to say what is an outlier and what isn't, but this is definitely an observation that is quite a ways away from the typical. So these whiskers go out. This one is going out to 1.5 times the quartile range, less than the median, and this is going out to something less than that because there are no data points out here. Yes?
Why does it go?
Good question. Yeah, why 1.5 times the quartile range? It's completely arbitrary. It's customary. It's convenient because when you see a box plot, you can probably assume that it's going out to 1.5 times the interquartile range. But there's probably an option in there to change that. You could change it. Yep.
I was going to ask about sometimes the bars are 5th and 95th. Is that just preference? Or?
So are you talking about confidence intervals?
Well, in like some of the graphing statistical packages, they give you an option of doing a box plot with 5th and 95th.
5th and 95th percentiles. Yeah, so that would be different because then you would always have data points on the outside. I don't know. I've never made box plots like that. I like that. I consider this at least to be a standard, but you could. Yeah. The other nice thing is that this is also just a standard for when there's an outlier. If you are choosing 5th and 95th, then these are not outliers anymore. You're guaranteed to have 5% below and 5% above there. Any other questions? Where's the air conditioning? Another option is exact plotting of the data. This is actually often pretty useful, and you can do it in instances like this. This is a one-dimensional scatter plot here. This is just put a little line here where with each one of the data points, and that exact plotting can be useful. In this case, you can kind of see there's more density, but you find that in fact, sometimes having too much information makes the data less interpretable. You know, it's not as easy to see how the density of points increases in the middle here as it was with the histogram and that density line. There's all kinds of extra stuff that you can do. I don't even know how to make a plot like this. I could do it if you gave me all day, but someone here managed to put all of these together in one plot. So here's your histogram. Here are a couple of different density lines with different amounts of smoothing. Here's this strip chart with all of the exact points plotted and a box plot. So I just like this because it actually kind of helps to understand the relationship between all of these. These are all visualizing for you the same data. In this case, horsepower of cars, but you can see how they're these individual points that on the box plot are shown as outliers. Also on the density lines causing a bit of a bump. Yeah.
Could you just explain the box plot?
Yeah.
I'm getting it wrong.
Okay, so here, these are horsepower of cars. We've got from this super small car. This is a golf cart here. We have a bunch in the middle, and then we have some like sports cars up here. This is giving us a summary of all of these. So it's telling us that the median car is right here. The one that is right in the middle. Half of all cars have more horsepower, half are all less. The first quartile means that 25% of cars have lower horsepower than a car that's right here at 170 about
so you would
horsepower.
always need like a horizontal axis with a scale on it to help you.
Box plots can be either horizontal or vertical.
You need like a scale there.
But yeah, you need a scale. This is shown up against the scale here, so you can see that the median is 210. yeah, it's a visual and quantitative summary of a continuous variable. In order to be quantitative, it has to have this scale because it's telling you quantitative values like the median, the quartile, this range of median plus 1.5 IQRs. So it's about, this kind of looks like more than 1.5 IQR. But you're welcome. So, to wrap up, we covered the key types of data, starting with nominal and ordinal data, along with ways to summarize those, the frequency tables and the pie and the bar plots. For discrete and continuous data, we talked about how to, well, both to show them exactly. We're only doing single univariate visualizations today, so we did further discretization along with frequency tables, histograms, box plots, and those frequency polygons, and without further discretization, the strip chart, and once we get into bivariate data, the scatter plot. And I just wanted to point out to anyone who is interested in trying out R that I included as a file with all of the R code for all of the plots that I put in the lecture today. And with that, I'm going to wrap up the lecture before I faint and give everyone a 10-minute break, get a drink of water, and come back in here for the lab. If you have not yet signed the verification of attendance, please do it.
Make sure you sign it, you have to verify that you're attending.
Yeah.
So I'll leave this up front. You can sign it on the way out. Okay, let's take about 10 minutes. It's air conditioned out there, so if you feel you want to, you might as well take a walk back.